Yeah, first of all, I would like to thank the organizers for inviting me to give this talk. Yeah, my name is Juan Luis Verbena. I'm currently working at the University of Cologne and as part of the GREAT team. So I'm going to be talking about great data that is available already in the archive. Like Professor Meixner mentioned on Wednesday, there's a large amount of data in the archive that's ready to be downloaded and used by especially by the young astronomers. Then on Wednesday also we had a talk by a very nice talk by Luisa that showed the archive and how to get data using the interface. So in this talk we're gonna go from the process of downloading the data and then explaining what's in there and what one can do with it. First, I would like to just briefly introduce what the GREAT instrument is. So GREAT is a heterodyne instrument, is the German receiver for astronomy at terahertz frequencies. It's a multi-pixel high-resolution spectrometer for SOFIA. Basically, we have three arrays. We have the low-frequency array, which is consists of 7 pixels in a hexagonal array around the central pixel 0, and in 2 polarizations. So in total, we would have 14 pixels. For the high frequency array, we only have 1 polarization, so 7 pixels, and we also have 4 grid, which uses single pixel channels in the and the frequency ranges are the ones that are seen here. So from this point, I'm gonna move to a Jupyter notebook where I have all the with this all the steps that one can follow to examine the data that one gets from the archive. So first, I'm gonna start by doing the import stuff. With nothing special. So we have. Is this is this visible? I'm just curious. The Jupyter notebook.
Yes.
Yep, we can see it.
Perfect. So this typical stuff, NumPy, pandas, and I'm gonna show by the end an example using the working with FITS files or using SciGrid, and yeah, in case one prefers to work with FITS files. So basically, what this notebook is, where it does, we're gonna run some class scripts, and we're gonna see the output here. If we have an image, then it's gonna be shown here in the notebook, and also the content of the class terminal. The output we'll see here. We have some additional methods to just to download the file and to show the content of the. This is used to show what would be the output of the class terminal. So this notebook is available in the resources page of the school. So this can be used to download the data. From downloading to doing the first steps can be used as an initial step on to work with data. So we're gonna be downloading a map of like Luisa said, everyone observes Orion. So this is gonna be no exception. So we're gonna have download data from the Orion molecular cloud. This when you run this is gonna take some time because it's gonna download the data and then it's gonna extract it. So it downloads a tar archive from a tar file from the archive. Then it's gonna extract it. I already have it because I don't want to wait 4 or 5 minutes. So, but it's gonna take some time when you do it. Then okay, so what once we get this file, what's in there? So the data products in the archive are level 3 and level 4 data products. First, I'm going to start with the level 3. So the level 3 data contains fully calibrated spectra. This has been produced by the calibration program Calibrate from the raw counts from the level 1 data. And the level 3 are going to be 2 .grade files. So the first one is going to have the scientific target spectra in units of antenna temperature, and then additional output spectra, which is going to be related to the calibration. The second one, which I'm going to show later, it's going to have the only the scientific target spectra and corrected for main beam efficiency. So it's going to be in main beam temperature units. So the way this notebook works, we have this CMD string, which is the class command. I wrote it here simply like this, so it can be just copied and pasted onto a class terminal or into a file with a class script that you can run. So basically, this can be run in class just to have everything together here in the notebook. It's done like this. So we go into the file to see what's the content of this antenna temperature file. So it's gonna, when you download it, it's gonna be downloaded in this directory. So the data directory, it has long names, has the date and the flight name, then the project number, and then some additional numbers here. Then you have this is your .grade file. You can work with it in class. So let's see what's in there. Like I mentioned, so we have a bunch of spectra. So this is the source, the Orion molecular cloud. This is the source spectra. But then we have this additional spectra related to the calibration. Not all the projects have all this spectra, but what they do all have is the receiver temperature, the system temperature spectra, the observed and fitted sky, which are used to do the atmospheric calibration to correct for the atmospheric attenuation and to obtain the opacities. And these are also included there. So let's see what the receiver temperature spectra looks like. So we go into the file, we choose the spectra that we want to see. I put this number here because I already know that this is our receiver temperature spectra. Then we can see the output that class would give us. We have this the receiver temperature, which is like a measure of the receiver performance. Then for the system temperature, we do the same. So we can see here what the system temperature here. You can do this with your data to see the performance of the optics, the equipment. And here we want to see how good the fit of the sky was as compared to the observation. This is related to the atmospheric calibration, like I mentioned. So I know this is the sky minus hot observed, so the observed sky and the fitted sky, and then we can see here how good the fit is to the observed sky. You can also do this with the data to have an idea of how good the atmospheric calibration is. And yeah, in this case, I think this is all right. From the observed sky, by fitting the observed sky, one obtains the parameters like the precipitable water vapor, so that one can deduce opacities and correct for the atmospheric attenuation. This is what the tau, the opacity spectra would look like in this case for this data for this particular spectra. This is the first level 3 .grade file, the antenna temperature. But like I mentioned before, there's a second one which contains the scientific target spectra only and in units of main beam temperature. So in this case, I have a little script here that's going to convert the antenna temperature to main beam temperature. We're going to write this. We're going to write to a new .grade file. What's important to know here is that the pixels have different main beam efficiencies, so they have to be corrected by telescope. So what happens here is that we enter the values of the main beam efficiencies for each of the telescope in the order that they're going to be iterated through. Then we define a variable with that includes all the telescopes. Then we correct by telescope with the modify command, which is what's used to correct for the beam efficiency. So what we have there, once we run this, we will have the file with only the source spectra in main beam temperature units, which we go to see what's there, and then we see that we have now we have only the source, and this is going to be already in main beam temperature units. These are the two level 3 that you're going to find in the package that you download from the archive. This is usually already there, the file with the main beam temperature, but yeah, you want to change, you think that the main efficiency values are wrong, yeah, you can create your own file. Then yeah, the level 4 data. Level 4 data, it also comes in the archive. This would be a combination of level 3 data products. For example, when you have a single point experiment, so you are observing a position in the sky, you're integrating for a long time to see if you have a detection, which you sometimes will detect something, and sometimes you won't. And then you will have the average spectra in that grade files also. If you, on the other hand, you map an extended region in the sky, then you will have the data cube, or a .lmv that you can also examine in class. Here, an example of how you average the pixels. In this case, sometimes it is useful to have the horizontal and the vertical polarization separated, so that yeah, for example, when you have a very weak detection, but you think it might be something there, there might be a real detection, it can be useful to see both polarization separated. And if you see the line, or what seems to be a line, in both of them, then there's more hope that this is a real detection. If not, then this is most likely just noise. In this case, we go through we separate the telescope groups in two. So we go with the horizontal polarization in this part, and then for the vertical polarization in this part. So we run the script, and yeah, let's see what we have in here. In this case, we have 14. We're going to have 14 spectra, so we're going to have an average for each of the pixels. So and separated in polarization. So we have one spectra for the pixel 0h and 0v. They're separated, and so on for the other pixels. So what does this average spectrum? So what do they look like? They're gonna look something like this. So this is also this plot. The position of the spectra correspond more or less, or yeah, they're arranged like this in the sky also. So we start with pixel 0 in the center. Then this is 1, 2, 3, 4, 5, and 6. And we have here two spectra for each of them, one for the horizontal polarization and one for vertical. In this case, there are different colors. It's impossible to know which one is which, but like I mentioned, I use this all the time when we have a weak signal, just to see if it's likely that it's really a signal or just noise. Then but usually it's more usual that you just average everything together, the horizontal and the vertical polarization together, to have to have a better signal to noise. And then this here, we don't care about the H or V in the telescope, so we just go by the number. We average them together, and then we would have so what's in this file that we have now. We have only 7 spectra, so this is the average of all the spectra observed by the central pixel, either H or V polarization. This is for, and so on for the other ones. And what does this look like? Yeah, this looks like this. So we have now the average spectra with all of the both polarizations averaged together. Yeah, this is here is an example of another way to use the scripts in the notebook. So there's some flexibility here, so we can define the string, the command string, then use it as a dictionary to enter some other parameters here, like and run, and then yeah, in this case I did a go where to see where the observations were taken, and then also the group plot of the pixel, the average, the average spectra. Some useful routine in class to when you want to convert from brightness temperature to Jansky. It's Jansky subroutine. You enter the frequency and the beam size, and then you would get as an output the conversion factors. Then, like I mentioned, sometimes when you map an extended region in the sky, you would obtain an LMV data cube that you can work in class with. How is this created? Oh, this is created. This is an example of a script that creates a map. So we're gonna do the baseline so the baseline corrected spectra. Gonna send it to another file. It's gonna, in this case, it's gonna have the TMB base addition at the end. And the important parameters to create the map, well, the beam size, the diameter, the size of the cell, and the resolution. Then the command that creates the map would be XY map. And to examine the map, then you do let name, let type LMV. This is probably all of you have done this. And then in this case, I'm gonna do a go bit so that I can show the plot here in the Jupyter notebook. But you would do go view. You would have an interactive figure in class, and yeah, you would examine your data cube. So this data cube is being created now, and yeah, the map is going to be displayed here. Yeah, okay, because this is some of the channels. So the channels are defined here. So from 40 to 55, so 16 channels. The data the spectra were smooth. So this it's now like some of the central channels where there is more emission. With this, you already with this you have the data there. You can do a map. You can play with it. And this is just another example with when I have just one channel just to show more detail. Like I mentioned, sometimes some people want to work on FITS files. Sometimes the FITS files are also available in the archive. And well, you can create you can export the FITS from class. If what's in the database is this file exported from class, and it's you just import it and work with it like a normal class index. And this is this script here would create a FITS file ready to be worked with. I'm not going to run that because that takes time. So I commented it So I wouldn't run it by accident, but if you want to create the fits file, you would run these two cells. And yeah, here I'm going to show an example. Sometimes I work with some data using SciGrid to regrid the data to the spatial grid, right, ascension and declination in this case. And there's an advantage of working with fits in Python is that there's a lot of flexibility. There's a lot of stuff that you can do. And if there's time, I'm gonna show some examples. Here, I define this as a class and then use some methods to using AstroPy, the AstroPy fits to read the content of the header, and then some auxiliary methods to create an NumPy array or to pandas data frame. This is when you define the SciGrid, the regridding headers. The data mostly obtained from the fits header. Then here the gridding, and the data that, so the important part what you get is the gridded map in this case, and projected to the world coordinate system here. I ran this already because it takes a couple minutes, so I think it's ready to show the map here. So doing this, you already have the everything ready to also use SciGrid. So you work on your data directly in Python if that's something that you prefer. What's important to mention here is that the way that it is at the moment, you wouldn't have the spectral grid. So this is you have the grid in space, or right ascension and declination, but you have the channels as channel numbers. So the channel axis or the spectral axis has not been regridded to velocity or frequency. I usually use the header that I get from SciGrid and just add some parameters as a dictionary and use the spectral cube library. But there are some other tools that can be used. It depends. It's a matter of preference, and maybe even SciGrid itself can do this. I don't know. I have never done this. I just want to, okay, I'm going to go back to the presentation to show the last part. So yeah, this is an example of something that can be done with SciGrid. In this case, this data is it's good data. So here it doesn't show a big difference, but for example, here what I did is this is the map with all the observations, just everything and the map created. But sometimes there are some spectra that have low quality that you can need to be removed. Sometimes something went wrong with the equipment or something, and some spectra have to be taken out, or the quality will be degraded. So in this case, I applied a very simple filter for this example, where I removed the spectra that had an RMS larger than some value in a given window with no emission. So it's a window with only noise, and if the RMS is too large, then I remove the spectra. And in the map in the middle, it's the spectra that were removed. This spectra here did not meet the criteria of having a RMS lower than a threshold. And the resulting map is here. So like I mentioned, for this data, really there's no big difference because data is quite good, I would say. But there's some other instances where this makes a difference and gets rid of some artifacts that you can see in the image. And this is something that in class probably could be done, but it's much easier and straightforward to do with when you work with Python and with NumPy arrays and pandas data frames. And yeah, that's just I would like to finish. Thank, thanks again for the invitation. I would like to thank the organizers